Hello, Geography 231 students. Welcome to week 14, the final class. Well, the final lecture, not the final class. Welcome to the final lecture of Geography 231. We have another week between now and finals week. Next week, week 15, I've just set aside for students just to be able to work on projects. So there's literally nothing on the schedule next week. And I know that may be slightly controversial, but the reason I did that is if we were in class this semester, I would have scheduled several open lab periods, basically, where I'd give you the entire class to work on projects. You could ask me questions. We could work together one-on-one as much as possible. But obviously, that's not an option in an online setting. So I decided to set aside week 15 to not give you any assignments. You can, if you're missing any work, you can use the time to make up missing assignments. But obviously the intent is for you to be able to work on final projects, which are due in 2 weeks. If you look at the calendar, we are 2 weeks away from finals week, which is hard to believe. But in some ways it's hard to believe. In other ways it's been a long time coming, right? So we've had 14 weeks of an online class, which I'd never taught online before. You'd never taken online before. And so I think everybody paid their dues this semester. And so you deserve a week to not receive new assignments, to be able to finish work and get your final projects in presentation order, right? Get everything to a standard that you feel comfortable presenting to your classmates. So, and just to reiterate, yeah, so we are going to be presenting for finals week. We're going to do Zoom presentations, which I'm very excited about. Not as excited as if we had been able to gather in class to do this, which is what I typically do. Normally, I'll bring, treats, bring cookies or something, donuts or whatever, and we all sit back and enjoy learning about what our classmates had done over the course of the semester. In this context, you're going to be in front of your computer screen as if you haven't done enough of that this semester. But still, we're going to do some actual presentations. Everybody does a 5-minute presentation. I will actually do an announcement next week just to kind of talk a little bit about that. So do be on the lookout for next week's announcements, even though you're not going to have assignments per se. I still will sort of give you all a little bit of information about what I'm looking for in terms of the presentation. That'll still give you, about 2 weeks to be able to get that in the books, or about a week and a half, I guess. So without further ado, let's move on to this week's lecture, okay? And if I think of any other announcements, I'll come back to them. Okay, so this week, raster analysis. So as I mentioned last week, I had initially scheduled 2 weeks of raster analysis, week 1 and week 2, but the regression stuff just, it occupied a lot of time, and we had several different tools I wanted to go over and other things, and so I ended up bumping a week of raster analysis. So this is your only week of raster, but that being said, if you've already taken 232, we spent many weeks on raster in the spring, and if you are about to take 32 this spring, I'm actually not going to be teaching that class. I thought I was. I'm actually going to be teaching world geography and weather and climate next semester, so I will not be teaching 232. But that being said, if you are going to take it in the spring, you will get quite a bit of raster analysis in that class. The class basically covers modeling and raster, so two different schools of thought in GIS that don't necessarily always go together, but they certainly do integrate, and there's a lot of overlap. But at any rate, this is kind of, you can consider this your intro to raster analysis. You'll get quite a bit more next semester. And if you've already taken 232, you can consider this your refresher, right? This is a quick review that shouldn't be too out of the ordinary. Although I will say that there's a tool, this multiply tool that you do in the tutorial that I had never used in our class in spring. So it's something new for you if you have already taken this. So at any rate, raster analysis is this week's subject. Obviously, the tutorial, I did do a tutorial this week, and basically I did about half of this week's lab with you, so you can follow along as needed. The remainder of the lab needs to be completed. However, you do not need to finish the final section where it asks you to create a shareable web map and use Arc Collector. You don't need to do that section. Basically, you go up to, I think it's page 82, and then that's it. You call it, let me just verify that. Yeah, you work your way, by the way, it's the return of making spatial decisions using ArcGIS Pro. You're going to work your way up to page 82, save your work, and then I've got 2 deliverables I'm looking for basically an analysis of what you're working with in terms of Hurricane Katrina, then also a map that you create. But you do not need to do the ArcGIS Online stuff. All right, so upon completion of this lecture and lab, you should understand the difference between vector and raster data, the importance of image resolution and color bands, and raster analysis techniques like map algebra and image classification. All right, so first and foremost, vector versus raster. This will probably be some review for a lot of you. In the intro to GIS class, I'm sure you were exposed to the differences between vector and raster data, basically the data structure of these two types of data. But maybe it's been a while, so here's your review. All right, so the goal of GIS data and maps in general is to represent real-world objects as accurately as possible. There are two basic approaches to this, two different data structures that you will encounter in GIS, and there's vector data, or the vector data model, and raster data. And ultimately, if the goal is to represent the world as accurately as possible, that doesn't tell you you must use vector or you must use raster. You use whichever data structure is most appropriate for that situation. You use whichever data structure best communicates or represents the real world. Okay, so in the context of this week's lab and lecture, obviously, we're going to be talking about raster data. And sometimes raster data is the most efficient, effective way to communicate the data. We'll talk about some situations where rasters may be better than vector, but we tend to, maybe if you're in this sort of intro GIS world, we spend so much time with vector data. That's, points, lines, and polygons, XY coordinates. We might think that those are superior to raster data, but that's not necessarily the case. Raster has its own place in the GIS world, and there's actually so much you can do with it. And we're going to do just a tiny sliver of that, in this week's lab. So we have kind of representations of vector and raster data. Of course, the irony here is that these are both raster data, actual raster images, because any sort of image that is composed of pixels, and if you're looking at it on a screen, and these are probably JPEGs, they are basically just images, right? Collections of pixels. What makes vector data unique is that they're essentially just a bunch of XY coordinates sometimes connected by lines to create lines, other times enclosed to create polygons. But we're actually in a very rasterized world, right? So if you've got a cell phone and you take a picture with your cell phone, you're essentially looking at a raster image. Raster images are just collections of pixels together where every pixel represents some sort of numerical value, okay? But in the GIS world, we spend so much time with vector data that we might overlook raster. And I want to tell you, you shouldn't do that. Don't overlook raster. So vector features are stored as a series of x, y, and sometimes z coordinates. Features can have, as I said, points, three geometric types, points, lines, or polygons. No matter what type it is, they're all types of vectors. Vectors just basically indicate a point or a location in space. Object-oriented vector feature models are collections of points, lines, or polygons where every geometric feature is linked to an attribute feature in an attribute table. And so not only do you see the geometric feature, the point, line, or polygon, you also have the attributes that are associated with that geographic feature. All right. So here you can see a point is just one single XY coordinate. A line is a collection of XY coordinates, and a polygon is an enclosed collection of XY coordinates where it creates essentially a circuit and you return back to the starting point. So what are the advantages of vector data? The biggest advantage is the precision, okay? So vector data gives you very, very precise, potentially very, very precise XY coordinates. Think about spatial resolution, we'll say, of something that's projected in state plane zone 6, Southern California, that's accurate to like 6 decimal places. We're talking about a matter of feet, but down to multiple 6 decimal places, that could give you an accuracy of a matter of inches, right? So XY coordinates are very, very accurate. And that's not to say that raster data are not accurate, but raster data use a different method for georeferencing. All right, so if we're putting raster data on a map, so it tends to allow for perhaps slightly less precision at any given location, but overall raster data uses anchor points on the Earth that you can essentially align with other features on the map. There are ways of making raster data very spatially accurate, but the inherent benefit of XY data is that every single point, line, or polygon actually has a hard and fast coordinate on Earth. Okay. Another advantage is you can easily store many features and attributes. Vector data tends to be very small in terms of storage space. So unless you've got an attribute table with hundreds of columns or hundreds of fields, you usually can get away with having a shapefile or a feature class that's in the matter of 10 or 20 megabytes tops. Whereas when it comes to raster data, we're talking about gigs or even terabytes of data, right? Vector data is flexible for cartography. It's really easy to symbolize points, lines, and polygons, make different colors, different line thicknesses, label, so on and so forth. Raster data, you can change the symbology, but you can't necessarily label features because there's every single point or pixel in a raster, maybe one of millions, right? So every pixel can't get a label, right? Vector data is much more conducive to cartography. Vector data is ideally suited for certain types of analysis, especially precise locations, areas, lengths, and spatial relationships between two or more layers or feature classes. So what's raster data? We've talked about the benefits of vector. Obviously, you've had plenty of vector data, so why should we spend any time talking about raster data at all, right? This is an example of a raster. So raster data, also known as surfaces, is basically, it doesn't have a distinct shape the way that a point, line, or polygon does, but rather it's a collection of measured values or measurable values, okay, for any location on Earth's surface. And as I said before, every single pixel in a raster or a surface represents some numerical value. So we can call this a matrix. It's a matrix of equally sized pixels. So you have an x axis and a y axis, and anywhere they overlap, you represent some single point, right? I shouldn't use point, a single pixel in this overall surface. Each cell represents a unit of surface area, and that has to do with spatial resolution, okay? And a measured or estimated value for that location. So a very high resolution raster image, the pixels are going to be very, very small, right? They represent a physically small portion of the real world, right? A small one-to-one correlation. But no matter how big or how high or low the resolution, every single cell or pixel represents some observed or estimated value. So when might we be using a raster data rather? When it comes to measuring things on the Earth's surface, like temperature, elevation, perhaps precipitation totals, anything where a sensor is sensing what is happening on the Earth's surface. Okay, so data are displayed also using gradients to show change from location to location. So you might see something that represents elevation, where like green colors represent a low elevation, browns might represent increasing highlands, and then maybe whites represent the highest elevations, usually simulating snow, right? Or if it has nothing to do with elevation, you might have some sort of light to dark or red to blue color scheme that still indicates some sort of increasing or decreasing values. So here we have in the upper left-hand corner XY location. So we generally with raster data, it's a georeference to some single XY location, and then anchor points are used to increase spatial accuracy. So here's a grid representing what the raster looks like, and here could be an actual raster. So unlike a vector polygon, which can contain a virtually limitless number of data points, when you say data about the feature, which is stored in fields, each cell in a raster has only one single attribute, and that's its value. The value is just some sort of numerical number. As I said before, it could be representing temperature or elevation, some sort of RGB value, infrared color. Oftentimes, if it's an actual RGB sensor, it's just taking a picture of their surface. But even that, using the term taking a picture kind of oversimplifies it. It's sensing the spectral signature from whatever it's looking at. Okay. So each pixel contains one single numerical value. So in a vector file, you could have like a street data set that has a street name, the street type, the city that the street's located in, the state, the county, whatever. With the raster data, it's just one single value. And values represent, some property of that pixel's area. And values may be integers or floating point numbers, so whole numbers or floating point numbers. As I said, only one numeric attribute can be stored per raster. If more than one attribute needs to be stored, a new raster has to be created. So what are some raster data usages? Some analyses are best suited for rasters, for example, hydrological modeling, so models that take elevation into account, elevation measurements, solar radiation measurements, so things that have to do with incoming solar radiation because there's some sort of intensity measurement from light to dark, slope analysis, looking at changing numerical values from cell to cell, bathymetry, which is the essentially topography of under the water, the ocean floor, and then map algebra. And map algebra, you're actually going to do that in this week's lab. Basically, since rasters are collections of numerical values, you can take two rasters and you can add them together. You can subtract, you can multiply, divide. You can just do basic math, more complicated math. But because it's just a collection of numbers, you can treat it like one big matrix and treat it accordingly when it comes to math. So there's just a couple of examples of what you might do with raster analyses. Density, so you can make a density layer. If you've got a point file, you can make a density layer. Distances, so because rasters are collections of numbers, you can obviously figure out distance from point A to point B. Interpolation, so if you have a data set, you can interpolate the values between observed points. Least cost method, that also relies on elevation, topography. View shed, that has to do with what can be viewed from a given location on a raster, and then buffers. So we tend to think of buffers in terms of vector data, but you can also buffer with rasters as well. Okay, types of raster data, continuous and discrete. What is that all about? So on the left-hand side here, we've got two examples of continuous rasters. Continuous rasters are essentially rasters where the values of pixels change continuously over space. Okay, what does that mean? Well, think about a photograph. With a photo, if you've got a picture taken, it's highly unlikely that two cells right next to one another are going to be the exact same number. Why? Even with like skin tones, for example, skin tone might be a little darker here, a little lighter there. Think about a photo of a forest. It may all be green, but there's going to be variations of dark green, light green, so on and so forth. So continuous raster, basically just think of that as values continuously changing over space. Contrast that with discrete rasters. Discrete rasters are essentially rasters where cells are classified into a limited number of values. So instead of them being any number from, we'll say 1 to 1,000,000, they're limited to like 1 through 5 or 1 through 10. And so the cells that are there sometimes have to be reclassified to meet those numbers, or they may just fall into the category by default. Say, for example, if we have like an old parcel map that's been digitized, that parcel map might just have black and white colors, and every single parcel could become one single discrete value, essentially. Okay. So continuous rasters store surfaces or fields of variables that change continuously over space, many potential values, not a limited number like discrete. An example of a continuous raster would be a digital elevation model known as a DEM. Digital elevation model has cells or pixels, each one representing a single elevation point. Okay, so in this case here, it's not a photograph, it's actually every cell represents an actual elevation. Okay, and so think about the mountains. From one point to the next, you're unlikely to find a very flat surface in the mountains, right? And so that means that the numerical values are continuously changing over space. This example here, we've got the lowest values represent 500 feet, the highest values represent 1,800 feet. And so it's continuously changing from that 500 to 800 range. Discrete rasters, as I said, essentially store features, but in raster format. They have relatively few values that change abruptly from one category to the next. And as I said before, sometimes data sets or rasters have to be reclassified so that every single cell value falls within the predetermined number of categories. So each color here represents a different value of a nominal scale field, denoting land cover class. So nominal scale tells you that it has a name, but it does not have a value, not an intrinsically valuable number. So it doesn't look at actual. You couldn't you could do map algebra. You couldn't actually measure what these different fields are in terms of actual numbers. They don't represent elevation. They don't represent temperature, anything like that. Every single one of these numbers actually has a name associated with it. And so that tells you is that this is qualitative. These are qualitative values, okay? So nominal values have no numeric value, and they represent features. So in this case here, the number 1 is associated with mixed conifer forest, and there happen to be 14 cells that are value 1. Value 2 is Douglas fir trees. 13 cells have a Douglas fir designation of 2. The value 3 is oak savanna, and value 4 is grassland. All right, so this probably, well, in this case, obviously it's just a model, but what this might represent is a photograph or an aerial photo where every different land type has been forced into one of these 4 land cover types. And you're actually going to encounter classified data in this week's lab, okay? And so you'll have a better understanding of what image classification is and how a photograph can actually be limited in the number of pixel values that are allowed to be displayed. Okay, raster bands. Raster bands. All right, so image values represent a brightness. Basically, we call them digital numbers. So every single, and this is specifically in the context of continuous rasters, okay? In aerial images, satellite images, every pixel is associated with a brightness number, what we call a DN, a digital number, from 0 to 255, okay? The first 3 bands correspond to blue, green, and red, and you need those 3, at least those 3 bands, to have a color image, okay? So there's also near infrared, mid infrared, and thermal bands as well, and those bands are not necessary for a true color image, but they do allow for further analysis, for land cover analysis, wildfire tracking, things like that. So there are 3 main ways to display a single band raster: as a binary image where every cell is either 1 or 0, and that's obviously going to lead to a black and white image. This type of display is often used for displaying maps with simple line work, such as parcel maps. So if there's an old hard copy parcel map that's been digitized, it may be a binary image because all it is black and white, right? Another way to render a single band raster is through grayscale, where each cell has a value of 0 to some other number, such as 255, that would be 8-bit, or 65,535 in a 16-bit image. And these are often used for grayscale aerial photos. And grayscale was really the standard for decades. Okay, so it really wasn't until the 1990s that you started to see more and more color images. Okay. Lastly, you can actually render a single band image as a color photo or color image using a mapping system, a color mapping system, where every numerical value maps to some RGB value. So a set of coded values is defined to a set of red, green, and blue, or RGB values. And so even though there's only one single band, and it's only going to be sensing one single value for every single pixel, there is essentially a crosswalk table where one numerical value is associated with an RGB value. So what's the data structure of raster bands? Well, a single raster may include multiple bands, as I mentioned before, and each band represents a small segment of the color spectrum. Okay, so in this example here, this is a 7-band image. All right, so 7 different bands. As I said before, the first 3 are RGB. Bands 4, 5, 6, and 7 are going to represent some non-visible light, so near infrared, mid infrared, or thermal. So that brings us to multiband. So multiband rasters, in that case, every cell location has more than one value associated with it. And these multiple values are sensed with different sensors, multispectral imagery, okay? So each band usually represents a segment of light spectrum collected by a sensor. Bands can represent any portion of the spectrum, including ranges not visible to the eye, such as infrared and ultraviolet. But basically, they're different image sensors sense different sections or bands along the color spectrum. So that's why we call them image bands, because they're little bands of light along this broader image spectrum, okay? So the term band originates from the reference to the color band on the electromagnetic spectrum, which looks something like this, all right? So the light that you, and this is probably review for a lot of you, but the light that you see with your eye is only a small sliver of the entire electromagnetic spectrum, okay? So on the one side, on the shortwave side, we've got cosmic rays, gamma rays, X-rays, ultraviolet rays, then we have visible light, and then the wavelength of light gets longer and longer and longer to the just outside of visible light. We have infrared, then we have microwaves, radar, radio, broadcast, and then long wave radiation, okay? And so the light that you see happens to generally range between 400 nanometers and 700 nanometers. And so all the light you see with your eyes falls within that small band or segment of the color spectrum. And so just to give you kind of I'm not going to spend much time on this, but this is just kind of a fun chart to give you some sort of association with these different wavelengths along the electromagnetic spectrum. Visible light, a wavelength of, we'll say, 600 nanometers is more or less the size of a bacteria, okay, or virus. And so it gets bigger as you scroll to the right here, smaller to the right, bigger to the left. And these bigger objects like the house and the soccer field and baseball are associated with the size of the wavelength of long wave electromagnetic sources, right? So AM radio, FM radio, microwave oven, they all have longer wavelengths than visible light, X-rays, and radioactivity. So here's an example of a composite image comprised of three different layers or color band images, red, green, and blue. And here is an actual real-world application of that. So again, this goes back to the idea of having digital numbers, 0 to 255. So in the red band of light, we essentially see that the R value is lower where it's darker, okay, and higher where it's brighter. With the green value, we see it once again, higher values tend to be lighter, lower values tend to be darker, and the same goes for blue as well. And if you overlay those together, you actually have something that approximates a true color image. All right, next up, resolution. So we've talked about color bands, talked about the importance of different bands along the color spectrum, but what about the actual cells, the actual pixels that you're viewing? Well, resolution has a lot to do with the accuracy, the spatial accuracy of the image. So just like a digital photo, resolution matters. So if you take a photo with your camera or your phone and then you zoom in as much as you can, you start to see pixels, right? Maybe your phone may limit the ability to zoom in, but on an older digital camera, you can zoom in all the way to the point where the pixels end up being big squares, right? And that's essentially what rasters are. That's why if you go into Photoshop, you can end up making little minute changes to photographs because all you essentially are working with are grids of individual cells. Every cell represents some sort of digital number, and you can change those numbers, and in turn, those numbers change the colors if it's a photograph, okay? So with lower resolution, we end up with what we call pixelation, and that's something everybody's encountered, right? In a digital photo. You zoom in too much, you see the pixels. So storage space increases by the square of the resolution. So the higher the resolution, we become exponentially larger in terms of storage size. So that's another one when I talked earlier about the benefits of vector versus raster. Raster data does occupy a lot of storage space. So portraying large areas at high resolution is potentially problematic for like your computer that you're using right now, right? So even in the lab at Cypress College, we end up always testing the abilities of those computers when it comes to raster data. Spatial resolution is a lot like DPI, so like on a printer, dots per inch. You can kind of imagine it like this graphic that I have right here. So rather than measuring the number of pixels within a square inch, we measure real-world distance equivalent to 1 inch. So 1 pixel equals 1 foot would be a lower resolution than 1 pixel representing 3 inches. Okay, so here's DPI, where this is 1 dot per inch, so literally 1 single pixel equaling a square inch. Here we have 2 DPI, so 2 dots per inch. Here's 5 DPI, 10, 25, 72, and 300. So as the number of dots per inch, or the resolution, increases, the crispness of the image itself increases as well. So how does that actually play out in real aerial imagery? Something like this. So right here we're looking at a 12-inch resolution. So 1 pixel equals 12 inches, or 1 foot. So 1 pixel in this photo represents 1 square foot on the ground in the real world, which is actually pretty good resolution, especially historically. If you take this in historical context, this is fantastic resolution. In 232, we talk a lot about spatial resolution, how multispectral imagery can be, certain resolution compared to like panchromatic imagery, which tends to be able to be higher resolution versus multispectral imagery. So what can you see in a 1 pixel to 1 foot resolution image? We can see pavement, we can see airfields, buildings, hydrology, forests, things like that. What might be used? What might this level of resolution be used for? Urban planning, detecting change over the landscape over time. So you could tell if a home was demolished or rebuilt. You could tell if a hole was dug, a big hole was dug. You can tell, basically changes. You can determine the prevailing land cover. Is it grass? Is it concrete? Is it forest? Is it water? This might be used in forestry management because you're able to tell, have trees been clear cut in this area, or have they regrown, so on and so forth. So that's 1 foot to 12 inches. 1 pixel to 12 inches. Here we have basically double the resolution. So in this case here, we have 6-inch resolution, where 1 pixel equals 6 inches. This is useful for viewing sidewalks and dirt roads, parking lots and driveways, lakes, ponds, streams, property lines. So telling where one person's property ends and another person's begins. In terms of practical usage, tracking land boundaries, identifying features on the landscape. So with this higher resolution, you can actually make out bushes and smaller trees. Natural resource management. Okay, so being able to see like, okay, these bushes look healthy, these ones don't. And also tracking irrigable land, which is really important in Southern California where we don't get a lot of rain. And finally, we have the highest resolution of them all. Well, in this data set, 1 pixel equals 3 inches. Resolution this high allows you to literally almost make out branches on a tree and almost even leaves potentially. So this with this resolution, we can see fire hydrants and manholes, branches on trees, power and light poles, curbs, traffic signs, single trees and shrubs, as I said. This is useful for civil engineering, 3D modeling, and volumetric analysis. So types of uses that rely on a high degree of detail. All right, and finally, the last section of tonight's lecture, map algebra. I need to cover map algebra. I know I've packed a lot into tonight. As I said, I probably would because I had to take 2 lectures and force them into one, and I apologize for that. But I want to cover map algebra tonight. And basically, it's the concept of taking raster layers and doing mathematical applying mathematical formula to them. Maybe it's 2 different rasters, adding them together, something like that. So basically, because rasters are just collections of numerical values, you can use them for math. So what is map algebra? Rasters, as I said, are essentially arrays of numbers. They can be added, subtracted, multiplied, divided, and so on. Lining up matching cells vertically, then line up matching cells vertically, then simple arithmetic or advanced algebraic functions can be run upon them. So the simple example I have right here, grid 1 has a collection of 4 numbers, 5, 7, 2, and 4. Grid 2 has a collection of 4 numbers, 3, 2, 1, and 6. Add these together, you end up with 5 and 3 is 8, 7 and 2 is 9, 2 and 1 is 3, and 4 and 6 is 10. So that's basic map algebra. But the thing that's important is that we start with two grids and we end up with a third grid. It actually creates a new layer, a new raster layer that can be symbolized, it can be used for further analysis, and so on and so forth. All right, another example of map algebra would be conversion, and you're going to actually do this in this week's lab. So you can convert, in this case here, precipitation measurements from centimeters to inches. In today's lab, you're going to convert from meters to feet. And so all you need to do in this case here is divide centimeters by 2.54 because there's 2.54 centimeters in an inch. In today's lab, you're going to go from meters to feet. So you're going to divide a meter by 3.28 because there are 3.28 feet in a meter. Okay, and so multiply a meter by 3.28 to end up with feet. So you can use map algebra for conversion. You can do what's known as cut and fill, which is basically a way of tracking change over time. So if you've got one measurement of the surface at one given time, and then you take that and you add or subtract a measurement of the same location at another time, you can see where the differences are, right? So this example here, we'll say there was a hole in 1980, that hole was filled in 1990, and so the difference between the two, we've got the filling and we've got the erosion, can be seen there by just doing simple subtraction. Initial minus new equals the difference. You can model equations. So map algebra allows for complex expressions with multiple inputs to calculate values. Here's an example. So hazard index. So landslide risk is based on 4 input grids: precipitation, slope, soil type, and vegetation cover. So essentially you have 4 different layers, and you can figure out however those are interacting together, you can create a more complex formula, right? So in this example here, it'd be precipitation times 1.5 plus slope times 2 divided by erosion minus vegetation cover. And the output is essentially an index. It tells you here's a value representing the hazard for landslide based off these 4 input variables. You also can use what's known as logical operators, also known as Boolean logic. Okay, so Boolean logic essentially is just asking a question, yes or no. Is this true or is it false? How does it do that? You set criteria, and if those numerical values meet the criteria, then yes, true. They pass. They get a 1. If they do not meet that criteria, false. They get a 0, and that just means that they don't fall out. They just are assigned a different numerical value. And so what you end up with is a binary, a 1, 0, yes, no, true, false binary. And so that tells you that for whatever the criteria is, these cells meet the criteria, these ones don't. The examples here are, so we have elevation over 1,200 feet. Is the elevation over 1,200 feet, yes or no? If it is, it's colored blue. If it's not, it's not. Is the slope less than 10 degrees? It's either yes or no. Is the canopy coverage less than 70% and greater than 40%? Yes or no. So these are known as Boolean operators or Boolean logic. Boolean rasters represent maps of true-false statements for a particular condition, and you will be doing that also in today's lab. Boolean operators can be and, or, XOR, which is exclusive or not. And there actually are other ones as well. Those aren't the only ones. But I won't get into this too much because it sort of goes outside today's lab, and I just want to make sure you're all covered for that. But just know that essentially what Boolean operators are a true. They create a true-false statement essentially. Does the criteria meet these premises or these requirements? If so, then yes. If not, then no. Here's an example of Boolean map algebra with ands. So and is like addition, okay? Or is it subtraction? Subtraction, sorry. Subtraction. Or not an exclusive or. And so essentially, depending on and or not or exclusive or, you end up with a different output raster in each situation. Here's a Boolean overlay, which is and. Okay, so this means that both of these must be true. So in this case here, we have precipitation is greater than or equal to 15 centimeters, and elevation is greater than or equal to 1,500 meters. 15 centimeters, 1500 meters. And then what you end up finding is a lodgepole tree habitat. So it has to be an area with enough precipitation and a high enough elevation. That's where you're likely to find these types of trees. Additive boolean. Okay, so in this case here, additive overlays add layers together to create a rank status or ranked result, kind of like an index. So you've got one input plus another input ends up with this third layer where you've got 0, 1, and 2. So it's not just the output is not a single yes or no. It's actually the aggregation of numerical values atop one another. The raster calculator is the tool that you use. The raster calculator allows you to use numerical formulas, add, subtract, multiply, divide, mathematical functions, sine, exponent, cosine, and the boolean operators, as I said, if, or, not, exclusive or, greater than, less than. And essentially, if it meets the criteria, it gets a 1. If it doesn't, it gets a 0. Okay. So hopefully that was a really fast, brief primer on how map algebra, raster algebra works. You're going to be using that in today's lab. So if you have questions, obviously, let me know, but hopefully that gets you to the place where you need to be just to at least understand what you're doing as you're walking yourself through the steps. Okay, so with that said, this week's lab assignment, as I've already mentioned at the top of the lecture, it comes from making spatial decisions, the return of making spatial decisions. This is module 2, part 1. And what am I looking for? I'm looking for 2 deliverables. One is an analysis, and this is actually on, I don't actually have the page. I should have pulled up the page in advance. It's on page 64, okay? So I've tweaked it just a tiny bit, so make sure you use what I post on Canvas versus what's in the book, but this is basically from page 64. So make sure you've done all the steps up to that point before you consider answering the question. So write an analysis describing the variables of Hurricane Katrina and their interrelationship. So how do the variables on the map, how are they interrelated? How do they affect one another? For example, how does barometric pressure affect the observable manifestation of a hurricane? So how does barometric pressure affect wind speed, impact, destructive potential? How does hurricane wind speed vary based on location over land or water? What happened as Hurricane Katrina made landfall and continued northward inland? Refer to your map as you compose your analysis. So make sure you use your map. Don't just answer these by Googling or taking out, kind of guessing. Actually work your way through it, and I think you'll be able to answer these questions based off of the attributes in the attribute table, the hurricane track that Katrina created, the corresponding barometric pressure data in the attribute, and so on. So I need you to come up with an analysis for that. And then second, I'm actually looking for a map. This map deliverable, I think it's deliverable 2. So it's a map of the flooded Mississippi coast after Hurricane Katrina. The map should include a table showing the percentage of total flooded land and acreage by land covered type. So I actually walk you through part of this, then you have to do the table on your own. Okay, so I'm looking for those 2. So you can put them in the same file. You can export your map to a JPEG and pop it into a Word file, or you can upload the PDF and enter your text as well. So. And enter it in the comment section, not as an actual assignment. Okay, so that does it for this week's lab. My voice is almost gone. This is the last, as I said, the last lecture. So I will have announcements for you in week 15, but this is the last lecture. Thank you for hanging with me this semester, everybody. And it was not ideal, but I think we made the best of it. So until we meet again, take care.